Hello, I'm Gianpietro Nigro, and this semester I work with a team on a project in robotics. This will be discussed in a few seconds, but first of all, I would like to introduce each of the members. So, over here we have Francesco.
Hi.
Andrea.
Hello.
And Alessandro.
Hi. The main goal of our project is to design a software which is able to simulate and control a robotic arm. In particular, to set the positions of the robot and the goal he has to reach, we use these usingArUco markers. By using the camera of our PC, we managed to compute the real-world positions of our usingArUco markers, in particular the robot, the goal, and the origin. A third usingArUco marker called the word is just used as a reference.
We choose to divide our project into three main steps. The first one consists in generating the code, which recognizes the usingArUco markers and computes their position. The second part was that of generating the URDF file in order to build a simplified model of the robot based on the real robotic arm we are basing our project on, and then this will be useful for simulation purposes. Finally, we exploited the software Moveit in order to control the robot and in particular to perform the trajectory planning.
Okay, Francesco, would you like to say something about the code we developed to recognize the usingArUco code?
Yeah, sure. So, this is the code that deals with the usingArUco markers. You can see that the main functionalities are implemented within the function that we defined here. If we go to its definition, we can see that it takes the images from the webcam, converts them to black and white, and detects the markers within those images. It describes each markers from the pixel coordinates of each corner, which are saved within this variable. We use the information regarding the projection of the markers in the images, together with the camera matrix, the coefficients, and the information regarding the dimensions of the markers themselves in order to retrieve the translation and rotation vectors describing the distance between the frame of the camera and the marker itself. We manipulate this information in order to obtain a quaternion from the rotation vectors, and we use this information, the translation and the rotation, in order to describe the TF transformation between each frame. We define a transformation starting from the word marker to the camera, and then from the camera to the other two. We use this information in the other steps. In this next video you can see one of the problems that we met while trying to implement the software. The frames are not stable, they flicker and rotate. We discovered that this is due to the fact that the distance between the camera and the markers is too great, and this leads to an improper detection of the corners. In order to solve the problem, we decided to reduce the distance between the camera and the markers. In this last video you can see that now the frames are stable and the markers are well detected. Another way to solve this problem could be to use bigger markers or a higher resolution camera.
The next part of our project was to write the URDF code. As we know, an URDF code is able to generate a simulation of our robot for visualization purposes. In order to do that, we had to write each link one by one with its proper dimensions and the dimensions of the collisions. And then we had to join each link together with a joint, where the joint limits and also the velocities are defined.
To start the simulation, we had to input these commands in the terminal. Once our bit simulation started, we were able to visualize the robot and move it thanks to the GUI, each joint one by one. The base joint, then the box flange, elbow joint, wrist flange, and then the effector, where a black dot was added to visualize the rotation.
It was also possible to move the robot with a randomized bottom into a random position, and we had a little bit of fun with that.
Lastly, we can now see our implementation of Moveit. We start by waiting for the translation between the robot frame to the goal to stabilize. We now use this transformation as an input for the function goToPose we implemented to perform the trajectory planning. We align the transformation from the robot frame to the goals one with the base link, which is used by the kinematic solver to compute the trajectory planning. In order to avoid numerical problems, we set a 1 cm tolerance over the position of the end effector. Since our only interest is for the TCP to meet the goal's origin and not to have the respective frames coincide, we impose a rotation tolerance greater than 2π, otherwise almost no solution could ever be found. We now require the software to compute the trajectory and, if it is found, we now execute it. For this node to run, all the auxiliary components need to be running in rows. This can be easily done running the launch file generated during the Moveit initialization procedure.
As you can see, we can now start the program by pressing enter from the terminal. This is the moveitcommander.py program. And now we can see that it printed the position of the goal and it already computed the trajectory, which is being displayed, and it's slowly reaching the goal. As you can see, the goal is slightly moving, but it's perfectly acceptable and the TCP reaches the position quite effortlessly. The base link coincides with the robot pose and it's fixed within orbit, so it's not moving, while the goal moves slightly but is perfectly acceptable.